The idea of chemical equilibrium is to me both interesting and somewhat disconcerting. What's disconcerting about equilibrium and its relationship to thermodynamics is that nature, the universe, has a preferred position for every chemical reaction that's out there, even those that would be, for example, hugely beneficial to humanity if they ran 100% to completion. A very important part of being a practicing chemist is learning how to outsmart equilibrium. How to drive a reaction towards the products you want, even under circumstances when thermodynamically that may not be the favored situation. Our guiding light when trying to outsmart equilibrium is an idea known as Le Chatelier's principle. And in this video we're going to lay out Le Chatelier's principle in general terms and look at a couple of specific examples of how we can use strategic concentrations of reactions and products and strategic temperatures and pressures to push a chemical reaction in the direction we want it to go. So let's think about starting with the system in chemical equilibrium, and let's take our general reaction system of A, B, C, and D with the usual Kc expression. What happens if we spike the reaction mixture with A? So we started off in equilibrium, and then we dump additional A into the system. Well, since the concentration of A changed, and A is a reactant under these circumstances, what we've done is increased the molarity of A while leaving all the other molarities constant, and we've thus led Q to be less than K. We've essentially made the denominator bigger than the numerator in Q, right? Which means that Q is less than K when we spike with a reactant, with A. Under these circumstances, the reaction will proceed forward, consuming A and reestablishing Q is equal to K. So as A and B get consumed, eventually we will reach a state where we're back in a balanced situation and Q is then equal to K. To get from the state right after the spiking back to equilibrium, the rate of the forward reaction must be faster than the rate of the reverse reaction. Let's think about this on a graph of the concentration of A versus time. Let's put the molarity of A on the y-axis and time on the x-axis. Initially, we start with the system in equilibrium. That means the concentration of A is macroscopically not changing with time, even if there are some small fluctuations in the concentration of A. At the moment we spike the system with A, the concentration of A increases rapidly. And at this point, this is a non-equilibrium state. Hence, the reaction will spontaneously go forward away from the molecules of A that were added. We need to increase Q, and so the reaction will go forward towards C and D. This causes a decrease in the concentration of A as the reaction spontaneously proceeds forward. But since we added A into the reaction mixture, the final equilibrium state is not the same as the initial equilibrium state. Eventually we will reach equilibrium again. That's why this line eventually flattens out. However, this final equilibrium state, notice it's not the same as the initial equilibrium state. And in fact, what we've done is, if we think from B's perspective, we've actually consumed more B by spiking A. You could imagine if we added enough A, we could end up with, for all intents and purposes, no B left, because the entire denominator of the equilibrium expression would be dominated by the molarity of A, and the molarity of B would be effectively zero. So hopefully you're starting to see how we can use this spiking idea to drive a reaction forward. For example, we can consume B. If our goal is to consume B or produce as much C and D as we possibly can, we can use a spike of A to do that. Let's look at one more example of this. Consider starting off the same reaction system at equilibrium again and spiking with C, a product now. Well, now C changed, C increased, the molarity of C increased, and all the other concentrations remained the same. This causes the numerator of the reaction quotient to be too large. This means Q is now greater than K, and so the reaction will proceed in reverse. The reaction will proceed backwards, consuming C until a new equilibrium state is reached, at which Q equals K again. Note the similarity with the spiking A situation. The substance consumed in the march back to equilibrium after the spiking event is the added substance. It was A in the first example, and it's C in this example. The reaction system spontaneously moves away from the added substance, consuming it. Let's again look at this on a concentration versus time graph, but this time let's put C on the y-axis, that is the molarity of C on the y-axis, and again put time on the x-axis. In the initial equilibrium state, the concentration of C is constant. When we spike with C, its concentration goes up rapidly, and this situation at the top of the spike is a non-equilibrium state. And so the reaction will spontaneously proceed either forward or backward. What we find is that the added substance C slowly disappears in the march back to equilibrium, and eventually this line flattens out and we reach a new equilibrium state. A couple of things worth noticing. The new equilibrium state, or the final equilibrium state, is not the same as the initial equilibrium state, and the consumption of C here corresponds to the reverse reaction. Remember, the way we wrote the reaction was A molecules of A plus B molecules of B goes to C molecules of C and D molecules of D. As equilibrium is reestablished in this system, the rate of the reverse reaction must be faster than the rate of the forward reaction, since we are observing consumption of C as this line comes down. For both of these situations then, spiking with a reactant A or with a product C, we're seeing that adding a substance causes the system to move away from that substance. And indeed, removing reactants or products works similarly. If we remove, for example, A, the system will move towards A to compensate for that removal. These observations point to a general idea known as Le Châtelier's principle, and that's a picture of Le Châtelier in the bottom left-hand corner of the slide. His principle says that if a system in dynamic equilibrium is disturbed, or more formally we say is stressed by a change in conditions, the system acts spontaneously to counteract that change. So if we add a reactant, for example, the system moves away from that reactant by going in the forward direction. If we remove a product, then the system will move again in the forward direction to form more of that product and counteract the change. This means, as we alluded to before, we can drive a reaction forward to completion by doing one of two things, either removing the products or adding reactants. In either case, what we're doing is knocking the system from equilibrium into a non-equilibrium state such that Q is less than K. And in fact, that's what both of these have in common, removing products or adding reactants. In either case, we're making Q less than K, right, such that the reaction will go forward in a macroscopic sense. That's the beauty of Le Châtelier's principle. We can drive a reaction in the direction we want it to go in spite of nature's preference, in spite of equilibrium. This idea doesn't just apply to reactant and product concentrations. It applies to other thermodynamic variables as well, most notably temperature and pressure. Let's talk about Le Châtelier's principle in temperature, which is a little bit more complicated than meets the eye. The punchline is going to be very straightforward, but I want to take us through the derivation just to see really the influence of temperature on the position of an equilibrium. The complicating thing about temperature is that temperature causes the value of Kc to change, which leads to complications. But, on the other hand, we do know how Kc varies with the temperature via the delta G of reaction. To clarify, this is the molar change in free energy of the reaction. How do we know? Well, we can combine the law of mass action, which mentions temperature in the argument of the exponential, with the thermodynamic definition of delta G. So delta G of reaction is both equal to negative RT natural log of Kc. This is a rearrangement, by the way, of that exponential expression that we saw before. And we can set that equal to delta H minus T delta S, and just do some rearranging to see how Kc, the equilibrium constant, is related to temperature. It's equal to delta S over R, which doesn't have a temperature term and is just a constant, minus delta H divided by RT. So what we're finding here is that the natural log of Kc is proportional to 1 over the temperature. The constant of proportionality is negative delta H over R, and the y-intercept is delta S over R. So that proportionality is a little bit non-intuitive. The natural log is proportional to 1 over T. So to make this a little bit more clear, let's differentiate both sides by the temperature to see how the natural log of K changes with temperature. More specifically, we're going to focus on the sign of d natural log of K dt to see this. So when we do this differentiation, we get that the derivative of the natural log of Kc with respect to temperature is equal to the derivative of the right-hand side, the derivative of this with respect to temperature. This delta S over R simply drops out since there's no temperature in there, and differentiating the second term amounts to differentiating negative C 1 over T, which is going to give us positive C 1 over T squared. And so the derivative of the natural log of K dt is equal to delta H over R, this is that positive C in the derivation over here on the right, divided by T squared. If we don't like the fact that natural log of K is appearing in here and we want to know how K itself varies with temperature, then we can do a little calculus, use the chain rule, and figure out that dk dt is equal to delta H over RT squared times Kc. Now, Kc will always be greater than 0. The temperature will always be greater than 0, and R will always be greater than 0. So the only thing impacting the relationship between K and temperature, and in particular whether K increases or decreases with temperature, is delta H. Let's think about this mathematically. If delta H is less than 0, that means that the derivative of K with respect to temperature is less than 0. That means Kc decreases with temperature. On the other hand, if delta H is greater than 0, that means that dk dt is greater than 0 and Kc increases with temperature. Here it is on the slide. If delta H is greater than 0, Kc increases with temperature. That's for an endothermic process. That's why this is written in blue. And if delta H is less than 0 for an exothermic process, Kc decreases with temperature. The trick now is to understand how increasing or decreasing K affects the position of the equilibrium, affects the concentrations of products and reactants at equilibrium. And if you understand, for example, how Q works, then it should be fairly intuitive that from the equilibrium expression, we can derive how the concentrations of reactants and products are going to change with the change in temperature. So for an endothermic reaction, increasing T causes Kc to increase. In that case, if we start out in equilibrium, Kc ends up having a larger, for example, numerator than the original Kc. So let's write P a little smaller to indicate that it's a little smaller in the initial case. When we increase T in this situation, because the reaction is endothermic, that's going to raise K, which is going to make the numerator larger. But if we started in equilibrium, then Q is equal to this. This implies then that Q is less than K, and the reaction will go forward. One way you'll often see this conceived is for an endothermic reaction, the reactants need, for example, heat to react, and so we can almost think of heat as a reagent in its own right. When we add heat for an endothermic process, that will drive the reaction forward, since we can sort of imagine heat as a reagent. That's not theoretically accurate, but it's consistent with this theoretical picture that we've developed so far. For exothermic reactions, increasing T causes Kc to decrease. So let's think about this systematically, just like we did for the endothermic process. If we think of the original equilibrium constant as products over reactants, and we imagine our system in that equilibrium state initially, when we go to raise the temperature, the new Kc decreases relative to Kc prime, and so we're going to have a larger value of the denominator than we started with. This means that Q will be greater than K in this case, and the reaction will proceed in the reverse direction. And again, the sort of intuitive picture you can develop here is for an exothermic reaction, the reactants release heat, so we can think of heat as a kind of product. As we increase the temperature and add heat, we're adding a quote-unquote reagent to the product side that's going to drive the reaction away from that added quote-unquote reagent back towards the products. So the punchline for Le Chatelier's principle in temperature is fairly straightforward if you think of heat as a kind of reagent. Increasing the temperature causes the reaction to spontaneously move away from the side where we find heat.